Hey everyone, Gene here. Welcome back to Do Some Dev. Today we're diving deeper into the world of Java multithreading. We're going to explore some powerful synchronization tools that can help you build more efficient and reliable concurrent applications. This is the 7th video in our Java multithreading series, so if you haven't checked out the previous ones, head over to the Java Advanced playlists. Let's start with a countdown latch. Imagine a group of runners waiting for the starting signal. A countdown latch is like that starting signal. It holds a certain number of permits. When all permits are required, the latch is released and the waiting threads can proceed. How does it work? Well, a countdown latch is initialized with a specific count. This count represents the number of permits. When a thread calls the await method, it's essentially acquiring a permit. The thread then waits until the count reaches 0, meaning all permits have been acquired. Once the count reaches 0, the latch is released and all waiting threads can proceed. Let's create a code example for that, with runners first all running towards the yellow finish line, then all waiting for each other, and then having a second run towards the red finish line. And just so you know, all the codes in this video can also be found on GitHub. You'll find a link to the repository in the description of this video. Alright, let's build ourselves a countdown latch example. For that, we create a new class, public class countdown latch example, implementing runnable. And the first thing that we define ourselves is a new variable, private final static int, thread underscore qty, which means the thread quantity of 3. Now let's define ourselves a run method. And in here we define ourselves all the countdown latches. So let's start with the first one. Final countdown latch first starter signal, with a new instance of countdown latch to 1. Meaning that we only need to switch once in order to have the threads continue. Now let's define ourselves the second one, final countdown latch yellow finish line, and in the new instance countdown latch we limit to the thread quantity, which is 3. Let's also define a second starter signal, limited at 1, and a red finish line limited at thread quantity. Now let's define runner to-dos, which essentially is a runnable, defining a new run method, and in here we define all the to-dos that one thread does. So here we have the different phases that we want to define. Wait for the first starter signal, run to the yellow finish line, wait for the second starter signal, and run to the red finish line. Let's start with the first starter signal. As we want to print out a couple of things, let's define a method for that, so that we guarantee that it always looks the same way. So one thing that we want is the current time, then we also want the current thread name, and a message that we provide. So here we have the first message, wait for first starter signal. And after that we tell this thread to wait at the first starter signal. Now as soon as another thread will tell this thread that it can run now, it will start to run until to the yellow finish line. So let's print out a message for that. Then let's simulate some work, which is a random sleep time, somewhere between 0 and 1000 milliseconds. After having done so, we print another message, reached yellow finish line. And after that, we tell the yellow finish line countdown latch to count 1 down, which is ourselves. After that, we go to the next starter signal. There we print out the message, wait for second starter signal. And after that, we await the second starter signal. After starting from there, we will run until the red finish line. So let's repeat the process. We print a message for running until to the red finish line. Then we sleep for a random time between 0 and 1000 milliseconds. And after having done so, we print the message, reached red finish line. Then we count ourselves out of the red finish line countdown latch. And that's about it for this run method. Now let's define what the main process will do. So the first thing that we want to do is define a thread pool. After that, we want to add and run all threads. After that, we will count down for the race to the yellow finish line, followed by waiting for all the runners to reach the yellow finish line. Then we will count down for the race to the red finish line, followed by waiting for the runners to reach the red finish line. And after that we will shut down the executor. Alright, let's define the thread pool. Here we define ourselves a new executor service, which we limit to the thread quantity. Next we add and run all threads. For that we print a message, start race, and then within the for loop we execute all the runnables. And that's it, now we can count down the race to the yellow finish line. So let's first wait for a second, then we say ready, then we wait for a second, then we say steady, then we wait for another second, and then we say go. And after having said go, we tell all the threads waiting for the first starter signal that they can go. Remember, we limited at 1, so it's just waiting for us to count 1 down. Now the next step for us as the main thread is to wait for all the other threads to reach the yellow finish line. Remember, we set it at 3. After having done all that, we continue by printing out the text, all runners reached yellow finish line. At about this point, all the runners will wait for the second starter signal to count down. So let's do exactly that. Ready, steady, go, and then count down the second starter signal. Now we wait for all the runners to reach the red finish line, and once they have done that, we output the text, all runners reach the red finish line, and then we also print the race is over, and we can shut down the executor. Alright, let's go to the main method to create an instance of the CountDownLatch example and run it. And there we go. First we have the countdown, where all the runners run until to the yellow finish line, and then we have the second countdown, where all the runners run until to the red finish line. And after that, the race is over. So there you have it. CountDownLatches are a powerful tool for coordinating thread execution. By understanding their mechanics, you can create more efficient and reliable concurrent applications. Next up is the CyclicBarrier. Imagine a team of construction workers. They cannot start the next phase until everyone in their team has finished their current task. A CyclicBarrier is like a synchronization point for this team. It ensures that all workers reach the specific point before proceeding. How does it work? Well, you create a CyclicBarrier with a specific number of parties. Each thread reaches the barrier and calls the await method. The barrier waits until all parties have arrived. Once all parties are present, the barrier is released and all threads can proceed. The cyclic part means that the barrier can be reused. After all threads have passed the barrier, it resets itself ready for the next round of synchronization. Now, how would this look in Java? Let's take a look. Alright, so let's create a CyclicBarrier example. For that, we create a new class, CyclicBarrier example, implementing the runnable, to override the run method, in which we start by defining ourselves a CyclicBarrier, which we limit to 3. And once this happens, we print the text, all workers have reached the checkpoint. Now we create ourselves a for loop, which runs from 1 to 3. Here we start by defining a final int sleep time millis, in which we define the time in milliseconds that a thread will wait. What we will also do is create a new thread, which will first simulate some work and then wait for all other threads to group. Let's also print out a text for that, worker, and then the worker ID will start the work. Then we sleep for a certain amount of time. And after having done so, we print again another message, worker, and then the worker ID reached the checkpoint. After that, we wait at the barrier. And after the barrier has led us through, we print the text, worker, and then the worker ID, continuing work. And in every iteration of this for loop, we start a new thread. Now let's go back to the main method and create a new instance of the CyclicBarrier example class and run it. And here we can see that we start 3 workers, then all 3 workers reach the checkpoint, and as soon as the third worker has reached the checkpoint, we print the message all workers have reached the checkpoint. And after that, all of them continue their work. Okay. This is what there is to know about the CyclicBarrier. Now let's explore another powerful synchronization tool, the exchanger. Imagine a classic trade scenario. 2 people meet at the designated place to exchange goods. That's exactly what the exchanger does in the world of multithreading. It's a synchronization point where 2 threads can exchange data. Why use an exchanger? Well, exchangers are incredibly useful for tasks like pipeline processing, meaning passing data between stages of a processing pipeline, genetic algorithms, meaning swapping genetic material between individuals, and producer-consumer patterns, which in this case means a more advanced form of producer-consumer, where the producer and the consumer directly exchange data. Let's see a practical example of a producer-consumer pattern using an exchanger. In this example, the producer thread generates data and passes it to the consumer thread via the exchanger. The consumer processes the data and sends a confirmation back to the producer. This direct exchange of data between threads can be more efficient than using a shared buffer. Okay, now let's create the exchanger example. For that, we create a new class exchanger example that also implements the runnable interface, which brings us to override the run method. Here we start by creating a new exchanger for exchanging strings. And the first thread that we create is the producer thread, in which we first define a buffer set to PPP. And then we define ourselves a new while loop, which is always true, which first prints that the producer sends the buffer. which is currently PPP. Then we give this buffer to the exchanger, and whatever the exchanger gives us, we put into the same variable buffer. After having done so, we print what the buffer is now. Now let's create another thread, consumer, which essentially does the same thing, but the string buffer is CCC, and the print lines are set to the consumer. One for sending and one for receiving. Now let's start both threads and tell the main thread to wait for 5 milliseconds. That should be enough to get a couple of exchanges. After having done so, we interrupt both threads. Alright, let's go back to the main method and create a new instance of the exchanger example class and run it. And here we can see that the producer sends PPP to the consumer then receives PPP, and at the same time the consumer also sends CCC to the producer, and the producer also receives CCC. And all this back and forth until we interrupt the threads. Of course there can be more examples for the exchanger, but what do you think about this example? Are you ready for another powerful synchronization tool? A semaphore is a powerful tool for controlling access to shared resources. It's like a limited number of permits. Threads acquire permits to access the resource and release them when they're done. Now, why use a semaphore? Well, semaphores are ideal for resource limiting, meaning controlling access to a fixed number of resources, rate limiting, meaning limiting the rate at which threads can perform a certain action, mutual exclusion, which is ensuring that only one thread can access a certain critical section at a time. There are two main types of semaphores: counting semaphores and binary semaphores. The counting semaphore allows multiple threads to access the resource concurrently, up to a specified limit. The binary semaphore only allows one thread to access the resource at a time, acting as a mutex. Let's take a look at a code example where we allow a limited number of threads to acquire a permit to work, and after having done just that, they release the permit again so that other waiting threads also get to do some work. Alright, time to create ourselves a semaphore example. For that we create a new class Semaphore example implementing the runnable, which brings us to implement the run method. And the first thing that we want to do here is create ourselves a semaphore, which we set to handle 5 permits at a time. After that we create ourselves a new thread pool using the executor service, which we set to 10. Now we want to submit tasks to the pool. For that we create ourselves a new for loop running from 0 to 9, so that we create 10 submits to the executor. And in every iteration we tell the thread to request a work permit from the semaphore using acquire. Before doing that we print that we do the request, and after having received one we also print that we have a permit. Then we simulate work in terms of sleeping 1000 milliseconds. And after having done the work, we release the permit again by calling the semaphore release method. And we also print it to the terminal. After having submitted all the tasks to the pool, we shut down the executor. Now let's go to the main method and create a new instance of the semaphore example class and run it. And here we can see that we have a couple of requests, a couple of permits, and then a couple of releases. All this done in 2 steps. Now, why would there be 2 steps? Well, we defined our semaphore to be at 5, while having 10 threads to do something at the same time. Yeah, and 10 divided by 5 is 2. So 2 steps. So let's go back to the semaphore example and set the semaphore from 5 to 1. Now having 10 threads, we should have 10 steps. Let's run again the example. And there we go. Now we have 10 steps. Finally, we have the phaser. It's a more flexible version of the CyclicBarrier, allowing for dynamic registration and deregistration of threads. It's like a dynamic meeting point, where threads can join and leave as needed. Let's see a practical example of a phaser with 3 phases. With phasers, you can create complex synchronization patterns that cannot be easily achieved with other tools. Imagine a pipeline of tasks, where each stage has a variable number of threads. Phasers can coordinate the flow of data between these stages, ensuring smooth and efficient processing. Alright, let's create ourselves a phaser example. For that we create a new class, phaser example, implementing the runnable, which brings us to implement the run method. And the first thing that we want to define is a new phaser set at 3. We also define ourselves a new executor service, which we also set at a thread pool of 3. Now let's create 3 submits to the executor. For that we create ourselves a for loop running from 0 to 2, and in every iteration we create 1 submit, in which we start by pulling ourselves the thread name that we have, and then we simulate some work. Before doing so, we randomly define a work duration, somewhere between 0 and 1000 milliseconds. Let's also quickly create a print method for some output that will always look the same way, using printf to print the current time, a message, and the thread name. Alright, the first message is start work for the defined work duration in milliseconds. Then we sleep for this duration. And then we print again stop work of the duration in milliseconds. After having done that, we want to wait at the phaser. For that, we create another method, wait and print, which lets the thread wait at the phaser arrive and await advance method. And once 3 threads have arrived, the phaser lets 3 threads through. After having done all that, we need to shut down the executor. Now let's go to the main method and create a new instance of the phaser example class. After having done so, we run it. And here we can see that 3 threads start work and then sleep for different amounts of milliseconds. Then depending on the time that they slept, they reach the phaser earlier or later. And after all 3 reach the phaser, they continue from phase 1 to phase 2. And the process repeats itself. By understanding and effectively using synchronization tools mentioned in this video, you can build more robust and scalable Java applications. In the next video, we'll delve into the Java locking framework, so stay tuned for more exciting Java content. Therefore, don't forget to like, comment and subscribe for more. Thank you for watching and see you in the next video.